This video has a brief introduction to rational functions and will cover graphing rational functions examples 1 and 2 from notes. If you look on this sheet that I have up here, you'll notice that I have 6 different rational functions. You can tell they're rational functions because a rational function is a polynomial divided by another polynomial. So here we have a first degree over a first degree polynomial. Here we have a 1, which I guess is a constant polynomial, over a second degree polynomial, and so forth. I want you to notice the variety of different shapes. Notice that we have a vertical asymptote here and a horizontal asymptote here. Actually, it'd probably be easier if I just sort of drew them in. Here we have a vertical asymptote and a horizontal asymptote. Notice on the example 2, I have 2 vertical asymptotes and a horizontal asymptote. On my third example, I have a vertical asymptote still. But notice I don't have a horizontal asymptote. I actually have a diagonal asymptote, sometimes called a slant asymptote. Example number 4, I have a vertical asymptote. Now if that part wasn't showing, imagine covering up all of the place near where the asymptote is. What does the graph look like? It looks like a parabola. I actually have a parabolic asymptote. So the rest of the graph looks like a parabola. In this, the fifth one, I have 2 vertical asymptotes and I have a slant asymptote. And in my last graph, this one's really weird because notice I still have a value in the denominator where x shouldn't be able to equal -2, but I don't seem to have any asymptotes at all here. I just have a graph that looks like a line. That's a little bit puzzling. But we're going to talk about all of these different types of graphs. We're going to analyze, which means basically break down and look at in detail the different pieces that make up a rational function so that we can tell what these graphs are going to look like, or at least get a pretty good idea of what they're going to look like just by looking at the equations. So we're going to start out with example 1. Now this is an example of a function that is like what you did in your worksheet before, so this should be pretty familiar to you, and you probably even have some ideas about asymptotes and what it looks like. But I want to first start out by saying, what's one thing that you know about this graph? And hopefully you'll recognize some issues here. We know that x can't equal 3 because that would be an undefined number. So we say y is undefined when x equals 3. And when we say y is undefined, that means y cannot exist. Can't exist. So that means we have to indicate on the graph that there is no possible value for y when x is 3. So what I do is I find where x is 3 and I mark a dotted line, basically saying that is forbidden. There is no possible point on that vertical line because that would be a value of y for that value for an x equals 3. There are no values of y for x equals 3. You cannot cross a vertical asymptote. You cannot ever cross a vertical asymptote. That's because that number doesn't exist, and by crossing it you would make a number exist there. Now other asymptotes can be crossed, and we'll talk, and that might violate what you've always been told is true, but they can be. They just show what happens to the graph in the long run. So you cannot ever cross a vertical asymptote, singular. Okay. Now, secondly, what are some other key points that we can see by looking at just at this function? So one thing to think about is x and y intercepts. What happens when x equals 0? What happens to y? What value of x makes y equal to 0? So let's think about f of 0. When we put 0 into the function, we get 2 over 0 minus 3, which is -2/3. So I have the point 0, -2/3. That's my y-intercept. So I'm going to plot that point, 0, negative 2/3. And notice these, the grid here is that each box represents 2, so I'm going to make negative 2/3 would be about right in here. Now what about setting the function equal to 0? So 2 over x minus 3 equals 0. Well, if I were going to solve that, I'm actually going to kind of scoot this over. I know you can't do that. Nah, 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 nah. I'm going to multiply both sides of the equation by x minus 3 to get rid of what's in the denominator. And what I end up with is 2 equals 0. Basically saying there is no value of x that I can put in. And if you look at it, I think you can realize that. There's no value of x that I can put in that will make y equal to 0. In order to make y equal 0, the numerator of the fraction would have to equal 0. And the numerator can't equal 0. So I'm just going to write, if the numerator cannot equal 0, there is no x-intercept. Okay, so we don't have an x-intercept. All right, what else do we want to look at here? We've looked at x and y intercepts. We've got a vertical asymptote. The other thing we want to look at is what happens when x goes to infinity. What happens when x gets really, really big? So let's think about what happens when x goes to positive infinity. So I'm just going to put in a really, really big number for x. Okay, so let's do 1,000,000. So f of 1,000,000. Well, that would give me 2 over 1,000,000. I think I have enough zeros there. One more. Minus 3. Well, that's 2 over 99,999. I have trouble with this word. 999,997. So what do we know about this number? Well, I hope you notice that it's positive, and it's very small, very close to 0. What about if I put in negative 1,000,000? That would give me 2 over, actually, negative 1,000,003, which is a negative number very close to 0. Because when you divide any number by a really, really big number, then you get a number that's very, very small. So when I have f is equal to 1,000,000, so close to 0, but positive over here as I go to positive infinity, close to 0 but negative as I go to negative infinity. What that tells me then is that 0 is a horizontal asymptote. Because what's happening to x as y, or what's happening to y as x gets really, really big, it's leveling off to 0. Now, what happens when we hit the vertical asymptote? So I'm going along here, go through my y-intercept. I can't cross the vertical asymptote, so it either has to go up or it has to go down. But we know that if x is negative, actually though here, if x is less than 3, so let me look in here. If x is less than 3, then this is going to be a negative number. If x is greater than 3, then this whole thing is going to be a positive number. So we'll think of this. So x less than 3, f of x is negative. So that means I'm going to have to go down this direction. If x is greater than 3, f of x is positive. Now, if we pick a number really, really close to 3, x is approximately 3, then y is going to positive or negative infinity. Because when we get really close to 3, like x is 3.0001, we'd have 2 over 3.0001 minus 3. Well, 2 divided by 0.0001 is what, 2,000 to 20,000 probably. It's getting really, really big. So when we make x close to 3, we make the denominator very small, and the smaller we make the denominator, the bigger f of x gets, or the bigger y gets. So we end up going to positive and negative infinity as we get really close to x and y. And I forgot to draw on my horizontal asymptote here. So this is what this graph looks like. Now you think, hey, we just did a bunch of these. Couldn't I just think this is 2 over x minus 3 plus 0, and that tells me 3 is my vertical asymptote and 0 is my horizontal asymptote? Exactly. You could certainly do that. I want you to know, though, kind of the whole thought process of going through this, so that when we get to ones that don't look like what you saw on Friday, that you'll understand how to do this. Okay, let's look at this next one. F of x equals 3x plus 5 over x plus 2. Once again, let's think about, where's that vertical asymptote? Where can y not exist? Okay, so x cannot equal 2. I'm sorry, x cannot equal negative 2. That's our vertical asymptote, because we cannot divide by 0. If you divide by 0, you get an undefined number. So negative 2 is our vertical asymptote. Let's look at our zeros. If I put 0 in for x, I get 3 times 0 plus 5 over 0 plus 2, which gives me 5 halves. So that means I have the point 0, 5 halves. That's my y-intercept. So notice that these are by 2, so 5 halves is 2.5, so that's about right here. Okay, then what if I set the function equal to 0? 3x plus 5 over x plus 2 equals 0. Well, if I multiply both sides of the equation by x minus 2, I would end up with 3x plus 5 is equal to 0 times x plus 2, or 3x plus 5 equals 0. So notice it's sufficient for the numerator to equal 0. If the numerator equals 0, then I have an x-intercept. So I'm just going to solve this. 3x is equal to negative 5. X is equal to negative 5/3. So I have the point negative 5/3, 0. There is my x-intercept. Negative 5/3 is just a little bit bigger than negative 6/3, so it's right to the right of this asymptote, the vertical asymptote. So we have our vertical asymptote, things where y cannot exist. We have our x-intercept and our y-intercept. The last thing to look at is what happens to this function when x goes to positive and negative infinity. So let's put in a million, f of 1 million. What happens? We get 3,000,005 in the numerator. In the denominator, we get 1,000,002. That's approximately what? 3,000,005 divided by 1,000,002. Well, that 5 and 2 don't make a whole lot of difference. That's approximately 3. If x is positive, we've got a positive 3. Now if we do f negative 1,000,000, well, we're subtracting 5. So I'm just going to write negative 3,000,000 plus 5, and negative 1,000,000 plus 2. Well, when we have negative over a negative, we're going to still end up with a positive 3. So it's still approximately 3. No matter if x is positive or negative, we're getting close to 3, which means that in the long run, I'm going to draw a line at 3 here. Here's where 3 is. In the long run, the graph is starting to look like the line y equals 3. If I am... Now the question is it a little more than 3 or is it a little less than 3? Well, if we look at the first one, if we look at, let's say x is equal to, let's make a, I guess I need to kind of clarify what I'm saying. I know that this graph is going to run along the horizontal asymptote like this red line I'm drawing. But when it gets to, I'm sorry, the vertical asymptote, it's going to run along like that because it can't cross, so it has to go down because of where those points are located. But I am allowed to cross a horizontal asymptote. A horizontal asymptote just tells me the long-run behavior of the graph as x goes to positive or negative infinity. So two things could happen here. I'm going to draw this in blue. Either I stay underneath the asymptote and run along it like this, or I go above the asymptote but then come back and level along the asymptote. Either one of those things could be true. So which one is true? The easiest way to figure that out is just to plug in a point for x. Plug in a value for x that's simple to calculate. So let's just say let x equal 10. So if we do f of 10, we end up with 35 divided by 12. Is 35 divided by 12 bigger than 3 or less than 3? Because remember, this is the line y equals 3. So if I want to figure out, is this bigger than 3 or less than 3, we notice that slightly, oops, it's not what I meant to do. I'm going to erase that y equals 3 too. This is less than 3. So that means of these two lines, I'll get rid of that. It's not the one above, it's the one below. So this is the way the graph goes. It runs just below 3. Now, let's look at the other side. Where is this graph going to go? Is it going to go in this upper quadrant down here, or could it go along the lower quadrant? It turns out with a rational function, we could have either way. So we need to know which one this one does. So let's look at what happens. Let's pick a value that is smaller than where the vertical asymptote is. We know the vertical asymptote is at -2, so let's pick -10, for example. So I'm going to let x equal -10. So what's f of -10? F of -10 would be -30 plus 5, which is -25, over -10 plus 2, which would be -8. -25 over -8, is that bigger than 3 or less than 3? It's a little bigger than 3 because 24 over 8 would be exactly 3. So that means that I'm above the x-axis, above the line y equals 3, and then I'm going to be coming up to positive infinity. So there's my graph. Now, there's another way of approaching this problem, and that is to take the numerator and divide it by the denominator. So I'm going to do this using long division. 3x plus 5 divided by x plus 2. How many times does x go into 3x? Well, it goes 3 times. And when I multiply 3 times both of these, remember that I get 3x plus 6. And I subtract the whole thing, which leaves me with a remainder of -1. So how do I write this? Now, I want to just kind of, my thinking person over here, I think I did this on the notes before, but remember, if you write this as a mixed number, you do 3 plus the remainder, -1, divided by what you divided by, which is x plus 1. So I can write f of x as 3 plus -1 over x plus 2. So that is equivalent to the 3x plus 5 over x plus 2. There's my horizontal asymptote. The -2 tells me my vertical asymptote. So this is the same form as what you saw before. Now, some of my students said earlier, well, isn't that a whole lot easier? Yes, it is a whole lot easier, but I still wanted to talk you through the whole process so you understand all about asymptotes, all about how you can figure out these points by using some reasoning and some plugging in some key points, because some of them are going to get a little more complicated and you'll need to know those strategies. Well, I'm going to leave you for now, and the next time we come back, we're going to get to some even cooler graphs, so just hold on to your seats and you'll be glad you continued on with this.